Okay, good afternoon, lads and ladies. Um, we have a few things to do today. Mostly, though, I just want to give you a little bit more practice with the logarithm stuff we introduced and played with last time, um, and sort of show you some applications. Like everybody else, I'm having a hard time turning away from what's going on with the election, but we can do it for a few minutes here to talk about some mathematics, eh? Okay. So this is MAC1140, section 4. And today is the 4th of November. Today, I want to talk about solving. Whoa, focus, you son of a bitch, focus. At least try to focus. All right. Today we're going to talk about solving log and exponential equations. So a log equation, this is an equation where the variable is inside a logarithm, and an exponential equation, this is an equation where the variable is inside an exponent. All right, so they are what they sound like. A log equation is an equation where in order to solve it, you'll need to undo a logarithm. And an exponential equation is an equation where in order to solve it, you're going to need to undo an exponential. Your sort of basic log equation will be something like the log base 2 of x plus 1 equals, I don't know, 3. Kind of a very simple example. So the variable you want to solve for is trapped inside a logarithm. The way we undo a logarithm is by exponentiating. So to solve all log equations, the thing you need to do is exponentiate. Because that's how you undo a log. And you exponentiate using whatever base the logarithm is here. So this is a base 2 log. So I'm going to exponentiate base 2, meaning I'll put both sides in the power of 2. So the left-hand side becomes 2 raised to this stuff, and the right-hand side becomes 2 raised to this stuff. This is very different from squaring both sides. I want to make that clear. Totally different operation. I'm not raising both sides to the power of 2. I'm putting both sides in the power of 2, which is very different. Now on the left-hand side, 2 raised to the base 2 log of x plus 1, that's 2 raised to a base 2 log of some stuff. That's just going to be that stuff. And on the right-hand side, 2 cubed is 8. So then my last move would be to subtract 1, and I get x equals 7. So this problem already had a logarithm in it. So it's not like I'm not using a logarithm here. I was given a log equation. Exponential equations, the sort of thing I'm going to do on the right here in a second, you can use whatever base log you want to clean those up. But here, if you're starting with your variable inside a logarithm, you should exponentiate using whatever the base of the given logarithm is. Yeah, if they start with your variable inside a log, the move is to exponentiate, and you always exponentiate using whatever number the base of the logarithm that was given to you has. So if this was a base 5 log, I would have put both sides in the power of 5. So here, on the other hand, if I had a basic sort of exponential equation, something like 3 to the 2x minus 1 equals 12. This I could solve by taking whatever kind of log I wanted. So I could take the base 3 log or the base 2 log or the natural log on both sides. So here we will take logs. And yeah, here maybe I'll take the natural log. You can use whatever base logarithm you want. Most people just default to using the natural log because that's the one logarithm that everybody knows and loves, especially once you get to calculus. The natural log is really the only log that anybody ever messes with. And you can use the rules for logarithms to bring this power down front. So that would be 2x minus 1 times the natural log of 3 equals the natural log of 12. We can divide both sides by ln3. And then we can add 1, divide by 2. I can get that. So these are your kind of basic exponential equations, and these are your kind of basic log equations. All the other exponential and log equations can be boiled down to things that look like these. So the general procedure for handling either one of these is going to be to isolate the exponential or isolate the logarithm term, right? Like here I've got the log term isolated. Here I've got the exponential term isolated, and then undo whichever thing you need to undo. So if you need to undo a log, you'll exponentiate. If you need to undo an exponential, you'll take logs. We can look at some more complicated examples just to sort of get a feel. And I'll grab 1 or 2 from your homework here. Oops, sorry, let me see. Yeah, I was reordering some of those problems to get the harder ones towards the end for you. So the most part here, this stuff is all very simple, right? Like a basic exponential or a basic log. But if we want to look at something a little more complicated, do I have any slightly more complicated exponential equations? No, expand. It's all pretty straightforward shit, isn't it? Let's look at something like number 36 here. I'll write this down. We have the base 5 log of x plus 14 minus the base 5 log of x minus 2 equals 1. So if I want to solve this, first I need to get all the log stuff together into a single term. Right? My goal is to get this into the form of a basic log equation, which is the log of some variable stuff equals a constant. Which means I need to put these two logs together into a single log. And I've got a rule that lets me do that. This is the same as the base 5 log of x plus 14 over x minus 2. And the right-hand side is still just 1. So I'm using my rules for logarithms to combine these into this. And now I can exponentiate. Now I can put both sides in the exponent of 5. So let's say 5 raised to the base 5 log of x plus 14 over x minus 2 equals 5 to the 1. I'm exponentiating base 5 because my logarithm is a base 5 logarithm. The left-hand side here simplifies to just x plus 14 over x minus 2. And the right-hand side here, 5 to the 1, that's just 5. Now to finish things, I would bring the 5 over to the left, solve this just like any other rational equation. This is x plus 14 over x minus 2 minus 5 equals 0. The 5 I can multiply by x minus 2 over x minus 2, and I get x plus 14 minus 5 times x minus 2 all over x minus 2 equals 0. So that's x plus 14 minus 5x plus 10. That's minus 4x, and then 14 plus 10 is plus 24 over x minus 2 equals 0. So that means negative 4x plus 24 has to be 0, or 24 has to be 4x, which means 6 has to be x. And you should check that when you plug your answers in here, they make sense. Because sometimes these rules that combine logs or split logs, sometimes they change the domain. Which means sometimes the final answer you get here, maybe you get 2 or 3 answers, some of those might make the original expression undefined. Remember, logs are only ever happy if their insides are positive. So if any number makes the inside of a logarithm negative, it's out. So let's check, let's plug in. I'll have log base 5 of 6 plus 14 minus the log base 5 of 6 minus 2, that's 4, equals 1. So Fabrice, from here to here, I had a common denominator between this piece and this piece. The 5 here, I multiplied by x minus 2 over x minus 2. So I could put that into a single fraction with this guy. So that's 5 times x minus 2 over x minus 2. And then I wrote them in a single fraction in that one step. If I continue checking here, this is log base 5 of 20 minus log base 5 of 4 equals 1. And yeah, if you combine those, that's log base 5 of 20 over 4 equals 1. That's log base 5 of 5 equals 1, which is true. So this is good. But yeah, that step, the step going from here to here, is just having a common denominator between these two pieces, between this piece and this piece. Okay. Sure. Well, so to talk about how the domain might change as you manipulate these expressions, think about this, right? Log x plus log x should be the same as log x times x is the same as log of x squared, right? If we're just following the rules and not thinking too hard about things, this makes great sense. But over here, the domain is, well, you need the inside of the log to be positive, so that's just the interval 0 to infinity. Over here, you need the inside of the log to be positive, but now that's negative infinity to 0 unioned with 0 to infinity. So because these rules alter the algebra of the inside of the log, even though this is equal to this everywhere they're both defined, this guy is defined in more places than this guy is. So the simplest way to think of it is that those properties of logarithms are correct. They work great. There's nothing wrong with them. But sometimes if you are handed the output of one of those things and you don't know where it came from, you might end up trying to plug some things in that weren't valid in the original expression. Which means you just need to check your answers at the end. That's all. Just like in, let's see, if you've taken trigonometry, then you've encountered, probably in pre-calculus, not pre-calculus, in college algebra also, you encountered some extraneous solutions where you do some algebra steps and you get to some solutions. Then you need to check them in the end to make sure they make sense. Same sort of thing is going on here. It's possible through these algebra properties, or through these logarithm properties, to end up with so-called extraneous solutions. I don't want to beat you guys to death with this stuff too hard, but I'd like to try one or two more problems along these lines. Most of these are really very easy. Yeah, why not? Let's try an exponential equation. Yeah, why not? All right. So how would I solve this equation for x? Who can give me an idea of a good first step? Before I can take any sort of logs, there's something else I need to do. Before I take logs, what do I need to do? Yeah, I need to isolate the exponential. Right. So I want to take the log of this piece because I know that that will cancel nicely. So first I need to get rid of the 1. We do that just by subtracting it over. I get e to the negative 7x equals 13 minus 1 is 12. Now I can take logs, right? So first you need to isolate the exponential, then you can take logs. And the natural log is definitely the most reasonable thing to use here because the base is e. The natural log of e to the negative 7x is negative 7x times the natural log of e. And here we're in luck. The natural log of e is a really nice number. What number is that? Yeah, good. It's 1. So since the natural log of e is 1, the left-hand side is just negative 7x. So I have negative 7x equals ln 12, which means that x has to be ln 12 over negative 7. Not too bad. Another sort of fun equation like this be something like this. 2 to the x minus 1 equals 0, and 3 to the x minus 2 equals 0. Sorry, 2 to the x, I gave away the first step. 2 to the x minus 1 times 3 to the x minus 2 equals 0. What would be a good first step on this fella? I definitely want to isolate x, yeah. But how do I do that? Yeah, I have here two factors, two different things multiplying to be 0. So I can set each one to 0 on their own. Just like you do with polynomials. And now each one of those will give me a basic exponential equation. If I add 1 to both sides here, I get 2 to the x equals 1. If I add 2 to both sides here, I get 3 to the x equals 2. And now this guy is actually easy to solve, right? What power of 2 equals 1? This is x equals 0. Or you could get there by taking a log. Here, I can take the natural log of both sides, and I get the natural log of 3x equals the natural log of 2. The natural log of 3x is x times the natural log of 3. So that's x times ln 3 equals ln 2. And then I can divide both sides by ln 3. So I have these two solutions, 0 and log 2 over log 3. Any questions on this last example? You could have. It's just that we didn't, it was easy enough to spot the solution here. But if you wanted to, you could take the natural log and say the natural log of 2x is equal to the natural log of 1. This is the same as x times the natural log of 2 equals the natural log of 1. But the natural log of 1 is 0. So this is the same as x equals 0 over the natural log of 2. And 0 divided by anything is 0. So this one was easy enough to solve just kind of thinking about it or just looking at it. But you could have taken logs, and it would have worked out just as fine. We need to remember that the log of 1 is always 0, regardless of the base. This is a useful fact to remember. Which is equivalent to saying 2 to the 0 or anything to the 0 is just 1. But yeah, if you're just like grinding on the problem and you're not like looking at it big picture, if you don't take a second to back up and see it, you would grind through it exactly like this, just taking natural logs on both sides, same way you did here, and you'd arrive at the same answer. And either one is okay. honestly, I think the rest of this is fairly straightforward. So there's not a whole lot else here to explain. We can talk about calculating inverses for just a second. Let's do that. We're talking about finding the inverse of an exponential function. It's that same procedure that we learned way back in chapter 2. But now the equations that we're going to have to solve are going to be exponential equations. So, maybe I want to find the inverse where f of x is like 3 times 2 to the x minus 1, something like this. So the function I want to invert is an exponential function. So I expect that the inverse is going to have something to do with a logarithm. But it might be worthwhile just to see what this looks like once or twice. So remember, your first step here is to write y in place of f of x. So I'd write y equals 3 times 2 to the x minus 1. And then my second step is to try and solve for x. So I'd divide both sides by 3. I'd say y over 3 equals 2 to the x minus 1. And then I can take logs. Maybe I take the natural log on both sides. So I'd have the natural log of y over 3 equals the natural log of 2 to the x minus 1. So I have the natural log of y over 3 equals x minus 1 times the natural log of 2. And I can divide both sides by ln 2. And I get ln y over 3 all divided by ln 2 equals x minus 1. And then I can add 1 to both sides. So I get ln of y over 3 divided by the ln of 2 plus 1 equals x. And then remember our last steps here. We swap x and y. So I'd say ln of x over 3 divided by ln 2 plus 1 equals y. And then finally, say, okay, f inverse of x is this stuff. And you might be wondering, like, can I simplify this? Can I like put the ln of x over 3 and this ln of 2 together? They're being divided. And the answer there is no. No, I can't. There's no clean way to get these guys to interact. I can't like hope to cancel or put the inside fractions together or do anything like that. It's important when you're manipulating logarithms to use just the rules that I gave you last time. Only those rules, right? Those are the only rules that work. If there are other rules that worked, I promise I would show them to you. What else is there to say here? Really not much. There's one thing that we haven't talked about, and that's the change of base formula. So I'm going to show you that, and then I'm going to let you guys go. We're going to wrap up a little bit early today. What was the question there? I'm sorry, I don't fully understand. So where we found our inverse function does what work? Like finding the inverse of a logarithm? We can do an example like that. Yeah, it's the same four-step procedure. Write y for f of x, solve for x, switch x and y, and then write f inverse. But if you're going the other way, trying to invert a log, you'll get an exponential. Why not? Let's do it. So let's say find f inverse of x, where f of x, let's make it a natural log. Let's make it 1/2 times the natural log of x minus 1. So same sort of thing here. I want to find the inverse to this function. This function is some kind of logarithm, so I'm expecting the inverse to be some kind of exponential. My first step would be to write y for f of x. And then my second step is to solve for x. So here I'd multiply both sides by 2. I want to get the log alone. So I'll have 2y equals the natural log of x minus 1. And then I'd exponentiate using whatever the base of the logarithm is here. So the base of the natural log is e. So I get e to the 2y equals e to the ln of x minus 1. E to the ln of x minus 1 is just x minus 1. So now I have e to the 2y equals x minus 1. And we can add 1 to both sides, and we get e to the 2y plus 1 equals x. So now we can swap x and y. And then f inverse is just that. So it's not too bad, right? All these exponentials, oh, it's okay. So all these exponentials are one-to-one functions, and all these logarithms are one-to-one functions. We don't have to stress nearly as much as we did about one-to-oneness back in the section on like polynomials and power functions when we were inverting those. Just have to be careful with the algebra. So the last thing I wanted to show you is the change of base formula. Really, this is just a tool that allows you to rewrite a log of a given base as a log of a different base. I'll show you what the formula says. It says the base b log of x is equal to the base c log of x over the base c log of b. So if somebody hands you a logarithm in a base you don't like, and you want to change it over to another base, you can. Like the base 2 log of 5. If I want to write that as a natural log, I can write that as ln 5 over ln 2, just in terms of natural logs. Or if I wanted to rewrite it in base 5, I could write it as the base 5 log of 5 divided by the base 5 log of 2. Or if I wanted to write it as a common log, I could write it as the common log of 5 over the common log of 2. Here I'm using c equals e. Here I'm using c equals 5. And here I'm using c equals 10. But the nice thing about this formula is that you get to pick c. So you can change a base B logarithm into a base C logarithm where you get to pick C. So you can change one base log into any other base log. And kind of the take-home message here is that bases don't really matter all that much in logarithms. All the different logarithms are constant multiples of each other. Which is why most people prefer to just work with the natural log, because there really is no consequence to doing that. It works fine. You don't miss anything. All right. I know this is a little bit early, guys, but I think for what I gave you to work on this week, that's all I have to say. So you guys can kind of take a breather. This will be an easy-ish week for y'all. Next week, we're going to talk a little bit about applications of exponentials and logs, and we're going to get ready for the test. Yeah. So the test we were originally going to schedule for the 11th, right? But the 11th turned out to be a holiday, turned out to be Veterans Day, and that's no good. We can't do that. And on the same token, I don't feel it would be fair for me to rush the test to the 9th. Everybody does deserve a day of review. So I think the way we're going to have to end up doing this, I said I was going to vote, but nobody was going to vote for the 9th. Everybody was going to vote for the 16th. So we're going to do it on the 16th. All right, so next Monday, we're going to review. You don't have class next Wednesday because that's a holiday. And then the Monday after next is going to be test 3. Test 3 is going to be all on exponentials and logarithms and their applications. So on the 9th, we will review together and I'll do some application problems. We'll work a little bit more with notation, whatever you guys would like to do. And then 1 week after that, because we lose a day to the holiday there, we'll have exam 3. Now I might drop a little bit of study material for you guys online, kind of like we did the previous week we had a holiday, just so we don't lose too much time to that holiday. It's rough with these 2-day-a-week classes to lose a whole day like that. But it is what it is. We have to do it how we have to do it. The 25th? I don't think so. So traditionally, we do not here at Santa Fe close the Wednesday before Thanksgiving. I do have all the dates marked on the syllabus, but we can take a careful look here. So 20 to 21 critical dates. Oh, they don't have the holidays in there. Do they have them in here? Convocation, they should, yeah. September, October, November. Yeah, no. So college is open until 5 p.m. on Wednesday. We are going to have a class meeting on the 25th. Veterans Day, the 11th, whole college is closed. Exam the following 16th. Regular class day Wednesday, regular class day the following Monday, and then we will have class on the 25th. All right, the college is closed Thursday, Friday, and Saturday, but not that Wednesday. So good question, fair question. Any other questions? Cool. Okay, so take your time and make sure you've really mastered the logarithm stuff. I know that you've all seen this before, but I also know that it's easy to kind of squeak through college algebra without really learning this shit. On this exam, I will be checking to see if you've really learned this shit, meaning I'm gonna make you draw graphs of logarithms. I'm gonna make you find domains of logarithms. I'm gonna make you expand and contract log statements. I'm gonna make you solve log and exponential equations, all of those things. And all of those are gonna make up the full content of the test. So without strong skills here, there's no like, oh, I'm gonna hope for the test not having a bunch of logs on it. The whole test is logs. So make sure you work through this stuff. If the homework is feeling unreasonable or you're having a difficult time with it, I strongly recommend that you look at that packet. That packet I sent out has saved many of my students from log hell in the past. And consider coming by office hours or sending me an email or something like that. I'd be happy to work with you guys. Alrighty. All right, then I'll go ahead and let you guys go. Enjoy the rest of your afternoon. Try not to lose too much sleep over the election, and I'll see you all next time.